Okay, so today we'll be talking about a new way of talking about surfaces that's going to set the stage for what we're going to get into next week, which is doing integration on surfaces, similar to how we did integration on curves last week. So anyway, we'll talk about a couple of sections today. So let's just do a quick review of how we've talked about surfaces before. So the one way we've talked about surfaces is when you have z given as a function of x and y. And so that's what we call the graph of a function of two variables. And so the advantage to this type of expression is that it's an explicit expression for z in terms of x and y. So I'll say something about that in a second. But the main disadvantages of this way of describing a surface is that basically because z is a function of x and y, remember the whole idea of function is that you have only one output for each input. So you can only have one z for each value of x and y. So if your surface is something like an entire sphere, you can do the top half as a graph of a function of two variables. You could do the bottom half as a function of two variables, graph of a function of two variables, but you can't do the whole thing. And so that's one of the weaknesses. Another one of the weaknesses is that you have to be able to solve for z in terms of x and y. So we've seen a few times in this course that algebra can be difficult, if not impossible to do. And so there's some equations that you might not be able to solve for z in terms of x and y. Okay, and then what else? Another way of talking about a surface that we've done before is as a level surface of a function of three variables. So that's when your equation looks something like some function f of x, y, z equals some number k. And so the advantage to this approach is that it's a lot more flexible. For example, that sphere that we were talking about a minute ago that can't be done as a graph of a function of two variables because of vertical line test considerations, is perfectly fine as a level surface of a function of three variables. So it's more flexible in that sense. Also, it's more flexible in that you can have like way more complicated algebra going on. You can have equation like x squared plus y squared plus z squared equals e to the xyz. You're not going to be able to solve that equation for any of those variables in terms of the other two. So it's still a surface, but you're not going to be able to get z in terms of x and y. The only way to get z outside of that exponent is to take a log, but now you have z trapped in a log, and so you kind of just get stuck. There's no way to solve for z in terms of x and y. Okay, the disadvantage, I guess, is that it is only an implicit expression. So, with both these equations as they're written right now, you can't really, I guess the sphere isn't so bad because you could solve for z is plus minus the square root. But for something like this, I don't really have a way to generate different points on the surface. It's more of just like a test for whether or not XYZ is on it or not. It doesn't really give me a recipe for finding points in the same way that if I had an expression like this, I pick X, pick Y, immediately it gives me Z. It's more of a recipe for finding points on the surface. But something like this, it's not really a recipe for finding points on the surface. So anyway, those are our two ways that we've talked about surfaces before. Today, let's add a third way to talk about surfaces. And so this is going to be what we call parametric equations for the surface, or if you remember back in chapter 13, when we talked about curves, you have basically, you could talk about parametric equations for the curve or the vector equation for the curve. It was really the same information. Either you write it as a vector equation like this, or I guess technically parametric equations would be when you write it as three separate equations, component by component. But really, it's the same exact information, either presented as a vector or as three separate equations. And at this point, we don't really want to make a distinction between those two ways of thinking about it. But the big thing is that each of x, y, and z is given in terms of two parameters, u and v. And so if you look at this type of equation, it's a lot like what we did for space curves, which was, remember, we had equations of the form r of t, where each of x, y, and z was given in terms of t. And so now, if you remember back, like from the very beginning of this course, it's a little bit confusing because we talk about curves that live in 2D or live in 3D, or surfaces that live in 3D. So like this piece of paper, let's pretend it's, you know, infinitesimally thin. This paper, sure, it lives in 3D. It lives in our 3D world that we live in. But the paper itself, if we're pretending it has 0 thickness, it's really a 2-dimensional object. Like, it has area, it doesn't really have volume if we're pretending that it's very, very thin. And so that's what we want to think of as dimension, that a curve, there's a more precise definition of curve, but for this course, your definition of curve should just be, yeah, it's something that's one-dimensional. Whereas our notion of surface, there's, like I said, a more precise definition of what a surface actually is, but our intuitive notion of surface is it's something that's 2-dimensional. So basically the number of parameters or the number of degrees of freedom, whichever word you want to use, that corresponds to the dimension of the object you're working with. So for example, the surface of the Earth is basically a sphere. I guess it does have some bumps on it, but for the most part, it's 2-dimensional, and that corresponds to the 2 degrees of freedom that we use to talk about places on Earth, which is latitude and longitude, right? The fact that the surface of the Earth is a surface, is 2D, is manifested in the fact that we use 2 coordinates to talk about points on it. So anyway, the number of parameters is the dimensionality of the object that we're talking about. Okay, and so I guess let's just warm up and think about an example of how this corresponds to a surface. So let's say I have the parametric or vector equation. Like I said, don't worry about what you call it. It's the same information. So x is 2 cosine of u. I guess that's the first thing to remember with this, is that when you have your equation r of uv, or any time in this course where we have r is always the position vector. So the coordinates of a position vector are the components of a position vector are the coordinates of points, x, y, z. So anyway, this is our example. And so on some level, what you could do, and this is what happens if you were to use GeoGebra to visualize one of these parametric surfaces, or just your computer, if you're going to program it yourself, it's just going to take a bunch of u and v values that are in this domain that we specify and plug it into r of uv to get different position vectors. So, you know, you can always do something like that. Just make a little table. Obviously, we're not going to be able to do as many as a computer could do pretty quickly, but if both u and v are 0, then it looks like we get r of uv is 2, 0, 0. So I could draw the point with that position vector. So 0, 0 is our parameter values, and then it spits out x is 2, y is 0, z is 0. So that's a point. I could do u is pi over 4, and v is 0, and that's going to spit out, I guess, x is square root of 2, v is still 0, but then 2 sine of u is also square root of 2. So I get this point here. So yeah, pi over 4, 0 corresponds to the point root 2, 0, root 2. And then I guess I could do, for example, pi over 2, comma 0, and get 0, 0, 2. So just like we did with t-values when you were thinking about drawing these space curves, we could just, label the parameter values for various points. I could do, for example, u is 0, v is 1 to get 2, 1, 0, which I guess would be if this is x, y, z, I would get this point. So what was that? 0, 1 gives me 2, 1, 0. I could do u is 0 and v is 2. So I'm just picking different points in this domain over here and seeing what I get. So 2, 2, 0, which would be located here. And so on and so forth. So if you wanted to, plug in as many points as you want and just draw them. So pick a UV ordered pair. This equation spits out x, y, z. Okay, but it turns out, and so I guess this could be the best you could do if I gave you a really complicated equation. That, you know, your only hope for understanding what it looks like would be to use a computer to help you figure it out. But these equations aren't super complicated. Let's see if we can get a better idea of what this looks like than just picking random points. So I guess the thing I could see here is notice that x and z involve sine and cosine of u. So if I do x squared plus z squared, I get 4 cosine squared u plus 4 sine squared u, which Pythagorean theorem says is 4. So x squared plus z squared equals 4, you should remember, is the equation of a cylinder around the y-axis of radius 2. So this surface is a part of a cylinder around the y-axis. And then I guess thinking about it, it looks like also if I combine the fact that y is v, I'm getting the y between 0 and 2 part of it. And then in addition, if I think about what's going on as far as x and z go, the fact that u is between 0 and pi over 2, and it looks like u is essentially functioning as my polar angle, I'm really only getting, you know, the x and z both positive part as well. So it turns out that putting this all together, the surface that we're dealing with is basically take the cylinder, cut it off between y equals 0 and y equals 2, and then also only consider the quarter of it where both x and z are positive. So anyway, for this equation where it's not super complicated, you are able to deduce that this is what we're looking at. So you can always just do a table, plug in points, and see. For super complicated equations, that's probably the best you'll be able to do. But for this, we're able to understand it a little bit better. And so I don't want to move on from this example just yet. I want to illustrate a concept that's going to be useful for us. And that's going to be something called the concept of grid curves. Basically, grid curves, there's going to be 2 families. And they're curves obtained by freezing a parameter at a particular value. And so the key here is we're freezing one of them and letting the other vary. So the 2 families, so in this example, I guess for all examples for this, there's curves that you get by freezing u and by freezing v. And so what do I mean? By freezing u, it would be something like looking at the curve r of u naught v. And by freezing v, it would be looking at r of u v naught. for various choices of U naught for various choices of V naught. So let's do some grid curve examples of this surface that we're talking about. So the first one could be, for example, what happens if I keep U frozen at 0? So I substitute in U equals 0. And so I just do that to these equations. I'm going to get 2, comma, V, comma, 0. And so now if you look at this, who cares like what the name of the parameter is? This thing right here is basically an R of t equation where x, y, and z are in terms of one thing. So back when we did space curves, we called the parameter t. For this curve here, the parameter is v. I mean, who cares? It's 2, comma, v, comma, 0, which if you want to, you could write that as 2, 0, 0 plus v times 0, 1, 0. You could recognize that as the line equation through the point 2, 0, 0, and with direction vector parallel to the y-axis. So this red curve here that I just drew, that's the curve that has equation R of 0v. And I could do the same thing. I could say, you know, instead, let's freeze U at pi over 2. So in that case, I get, well, 0v2 if I substitute in to the equation. So that gives me this red curve here, R of pi over 2, comma, v. And I guess here in the middle, that's what I would get if I did R of pi over 4, comma, v. Okay, and then I could do the other family. So the first family is by freezing U and letting V be your parameter. The other family would be freezing V and letting U be your parameter. So in this case, I would get 2 cosine U, 0, 2 sine U, which is a quarter circle based on our restriction on U, our quarter circle in the plane y equals 0. So this first blue curve over here, that's the curve with equation R of U, 0. And then if I did it over here, it would be living in the plane y equals 2. So this is R of U, 2. And then like this one here in the middle would be R of U, 1. So if you go and look in the textbook and on the online homework, you'll see a lot of, you'll see these sort of grid curves on your surfaces. And what those are the curves that you get by freezing your, one of the parameters at a certain value and varying the other parameters. So you could think about, yeah, this surface is either made up by doing a bunch of these red curves sort of glued together. And I'm doing a bad job at drawing it. Yeah, something like that. Or it's made by gluing a bunch of these blue curves together. But that's the idea, is that you have, remember R of t, if you have one parameter, you get a curve. So get all these one curves, you get all these other curves, and they are on your surface. So that's the basic idea. So next thing we could talk about is Parametric equations for a plane. So plane is the simplest type of surface. So let's see if we can understand how to do that. And so I claim that it's essentially the opposite information we needed from chapter 12. So for 230 people, it's been a little while since you thought about it. 232, maybe you should go back and review a little bit. But remember back in chapter 12, we learned that the plane with the point x naught, y naught, z naught, and normal vector ABC has equation A times x minus x naught plus B times y minus y naught plus C times z minus z naught equals 0. And so the whole idea was the normal vector was perpendicular to the plane. So instead, for now, when we're talking about parametric equations, it turns out that we're not interested in a vector that's perpendicular to the plane, but instead vectors that point along the plane. And so I claim that this is the equation then. So to sort of explain that, this is the picture you want to have in mind. That let's say that I know this point here that's at x naught, y naught, z naught. That has position vector x naught, y naught, z naught. So remember, position vector just means you're starting it at the origin. So these are my x, y, and z axes. And so that point is on the plane. And so, okay, let's say that then the plane that I'm looking for looks something like this. And I know that vector A and vector B point along the plane. And so what you want to think of this equation as representing is take your position vector R naught. Maybe I'll draw a vector B so that it doesn't look parallel to R naught. Yeah, let me just do something like that. Okay, and so the idea is that by adding any multiple of vector A, then any multiple of vector B, that'll get you to some other point on this plane. So for example, let's say I have this point over here. This position vector, and let me try that again. Okay, that's pretty good. For the sake of argument, this would be R of 3, 1, which would be R naught plus 3 times vector A plus vector B. If I substitute in U equals 3 and V equals 1, because the whole idea is that, yeah, let's add 3 copies of vector A. Yeah, so I didn't do a great job. Let's see if I can fix this. Oh, never mind. Redo. That's 3 copies of vector A. And then a copy of vector B. That will get me to this other point on the plane. And so, okay, what's so special about 3? What's so special about 1? Nothing. I could add any multiple vector A, any multiple vector B, and that gives me this plane here. So that's the idea. And the cool thing is that it looks very familiar to how we did lines back in chapter 13. So remember when we were talking about, let's say, this line, the whole idea is that this would be your starting point R naught, and then maybe this green vector V points along the line. And the whole idea is that, yeah, there's only one direction that points along this line. And so you could add any multiple of vector V. For example, you could add 2 copies of vector V and get another point on the line, and so on and so forth. So parametric equation for a plane. parametric equation for a line looks very similar. It's just that a line only has one direction. A plane has two linearly independent directions. That's the language from Math 220. But yeah, that's the idea. So plane equation, back in chapter 12, you need to know this perpendicular direction. But for parametric, you need two directions that point along the plane. Okay, so next thing we could talk about is the tangent plane to a parametric surface. So let's say I have R of uv, and I have some point with position vector R of u naught v naught, and I want the parametric equation to the tangent plane. I can use this. And so the picture you want to have in mind, so this is why we talked about the grid curves. Let's say that my surface looks something like this. And let's say that, okay, the point I'm interested in is right there. So this R of u naught v naught, that's my position vector at the point I'm talking about. So through any given point, I have the grid curve from freezing u at u naught, as well as the grid curve I get from freezing v at v naught. So the red curve, the v is functioning as the parameter. The blue curve, u, is functioning as the parameter. And so if you think back to how curve equations worked way back in chapter 13, is we had this thing called the tangent vector, which pointed along. And so we called it r prime of t, but now we need to be a little careful which derivative we're taking. So on the blue curve where u is the parameter, this tangent vector is r sub u of u naught v naught. And then on this red curve, the tangent vector to the red curve is the v partial at u naught v naught. And so then the whole idea is that the dark blue and the purple vectors point along the surface and therefore point along the tangent plane. So I go back to this plane equation. I do point plus one parameter times one direction plus another parameter times the other direction. Those directions that are along my tangent plane are these partial derivatives of the vector equation. And then finally, if I'm looking for the normal vector, I could take the cross product. So if I do, I guess for the way I've drawn it, RU cross RV would actually be pointing down by the right-hand rule. But if I needed to know the perpendicular direction to that tangent plane, that's what I would do. All right, so let's do an example. Let's say I have the equation R of uv is u squared v squared u plus v. Find parametric equations for the tangent plane as well as the regular xyz equation for the tangent plane. Okay. So I know I'm going to need u and v partials. Okay, so RU so I haven't really defined this yet, but it's basically just what we did for R prime of t. You just take the derivative of each component, except now we're talking partial derivatives with respect to u and v. So do your partial derivatives of each component. And so I need to plug in, notice up here, u naught v naught into these derivatives. So is u naught v naught 491? No, 491 is xyz. So I have to do something that we had to do a lot back in chapter 13, which is find which parameter value spits out this given XYZ coordinate. So essentially, I need to figure out what value of u and v makes u squared equal to 4, makes v squared equal to 9, and u plus v equal to 1. And so essentially that's a system of equations that I need to deal with. And so presumably we will be able to solve this. If we can't, then I lied to you and that point isn't actually on the surface. So anyway, it looks like we get u squared is 4 means u is plus minus 2. V squared equals 9 means v is plus minus 3. And so putting it together, it seems as though we're going to need to take v to be 3 and u to be negative 2. And so once you plug in and check, you see that this u equals negative 2, v equals 3 does indeed give me the position vector of the point 491. So that's what I need to do here. So I need to do the u partial at negative 2, 3, which gives me negative 4, 0, 1. And then I have to do the v partial at negative 2, 3, which is 0, 6, 1. And so the parametric equation of the tangent plane, I just used t of uv just because r is already being used for the surface. So let's just use a different vector letter here. It's fine. So t of uv is let's say, yeah, so we have the position vector of the point we're starting with, 491, and then I have u times this first direction that's along the tangent plane plus v times this other direction that's along the tangent plane. So again, make sure this is what parametric plane equations look like. You don't have u squareds, you don't have v squareds. You have to get these numerical vectors that are at this point that we're talking about. I mean, they can change, as we see here, that, yeah, depending on what points u and v we're talking about, which point on the surface, these directions change because the surface is curved, it's not a plane. But for the tangent plane at a specific point, you have to get those actual numbers. Okay. And then for the regular equation, we'll use the fact that minus 4, 0, 1 and 0, 6, 1 point along the tangent plane. Therefore, their cross product, minus 6, 4, negative 24, is perpendicular to that. So whatever, you could take the parallel direction. Well, I guess I can only divide by 2. Or I'll divide by negative 2 to get 3, negative 2, 12. So I could set up the equation 3 times x minus 4 minus 2 times y minus 9 plus 12 times z minus 1 equals 0. So that's my parametric equation. This is my good old regular XYZ equation. All right, so that's that. Next thing we want to talk about is surface area for a parametric surface. And so the formula you're going to want to keep in mind is the length of the cross product of RU and RV. Okay, so why is this the formula? Let's see here. What I want to do is consider this little patch of the surface. So let's see here. I'm going to zoom in, might as well. Where I have R of U naught V naught is one of the corners. And then I'm going to let, I guess, let's have this one be V. So this is U naught V naught plus delta V is parameter values at that point. And then this one would be located at U naught plus delta U, comma V naught. And then finally this corner is U naught plus delta U, V naught plus delta V. So I'm focusing on a small patch. So look at a small patch. And so what I'm going to do is then say that the area of that small patch is basically the area of this parallelogram that I would get by just sort of straightening out and connecting those points like that. So I'm going to create this parallelogram. So area of patch is approximately the area of this parallelogram. And so the 3 points that we're talking about that define the parallelogram is U naught V naught for that position vector, R of U naught V naught plus delta V, R of U naught plus delta U, V naught. And then over here, that would be the 4th point in the parallelogram. It's not really important. Okay. And so we haven't, okay, I guess then what we have is the area of the patch is approximately the area of the parallelogram, where this vector is R of U naught plus delta U V naught minus R of U naught V naught. So these R vectors are always starting at the origin. But if I want to get the displacement vectors on the sides of this parallelogram, I need to do the vector subtraction, right? So that means that this vector here, that's R of U naught plus delta U comma V naught minus R of U naught V naught. And then similarly, this is R of U naught V naught plus delta V minus R of U naught V naught. So that's my two, those are my two vectors that are doing this parallelogram. Okay. And so I didn't even write it down, but these partial derivatives, I'll do it off to the side here. If I were to write down what RU of U naught V naught is, it's the limit as h goes to 0 of R of U naught plus delta U V naught minus R of U naught V naught all over, okay, I guess I won't call it h, I'll just call it delta U, that's fine. That all derivatives, remember, think back to Calc 1, is they're defined in terms of these difference quotients. That for the U partial, you're freezing V at V naught, and you're adjusting U by a small amount, and you're doing this difference quotient. So basically what that's telling me is that if I pick delta U pretty small, that this partial derivative is approximately that. So basically right here, this is approximately the area of, well, this side is about r sub u times delta u, and this side is going to be r sub v times delta v. So similarly, the v partial is approximately this difference quotient where you freeze u naught, let v change by some small value delta v, and you could rearrange and solve for these differences to get this right here. And then now you think back, area of parallelogram, that was the length of the cross product. So it's the length of RU delta U cross RV delta V, which then you could rewrite as RU cross RV, and then delta U delta V are just, you know, your scalars. So you could pull those outside, assume they're positive so that the absolute value of them is themselves. And then basically that means that the total area is basically you sum up a bunch of these patch areas or patch area approximations. And then you take the limit as delta U, delta V, go to 0, and that's where you get this double integral of the length of RU cross RV. So again, this is something, you know, you're not really going to need to do for a quiz or for an exam, but I like it because it reiterates this limit definition of these derivatives to tell you that the displacement between 2 points on these grid curves can be approximated by the derivatives, the tangent vectors on the grid curves. And then you're sort of straightening this surface patch into a parallelogram. And if you remember back in chapter 12, we learned area of parallelogram is related to the length of the cross product of vectors pointing along the sides. So anyway, that's the formula. And so I'm not going to do an example of that. I'll sort of leave that for study group and recitation. It's just a formula you're going to have to memorize and practice using. So then the next thing I want to do is go back to, we skipped chapter 15.5 a couple weeks ago because it also talked about surface area, and instead of talking about it as a separate thing, it turns out the content of 15.5 is really just a special case of what I just showed you now. So 15.5, if you go back to remember, we had different ways of talking about a surface. That was what we started off today. So 15.5 discusses the surface area of a surface when you're given z in terms of x and y. Okay, so how are we going to figure out that this is a special case of the formula we just derived for r of uv? So I'll talk about this again in a minute, but who cares what the parameters are named? So let's say I wanted to parameterize the surface z equals f of xy. So the whole idea of parameterization is that you have x, y, and z, each in terms of two things, u and v. So u and v is just what the textbook decided to use for the general situation. But you can name your parameters whatever you want. And so in this situation, I think it's particularly convenient to let x and y be your parameters, so that x in terms of x and y is just x, y in terms of x and y is just y, and then z in terms of x and y, that's where we use the fact that we know z in terms of x and y. So r of xy is x, y, f of xy is a perfectly good parameterization of this surface that we're talking about. So just like we talked about for curves, there's infinitely many different ways to parameterize any given curve. The same is true for surfaces, but this is sort of the laziest way to do it. It works. I have x, y, and z in terms of two things. X is x, y is y, z is f of x, y. So now we go through and take the x and y partials, take the cross product, you get minus fx minus fy, 1, so that the length of our x cross our y is the square root of fx squared plus fy squared plus 1, which that's what we're integrating here. So we just figured out this as a special case of this previous formula, that whatever your parameters are, take the partials with respect to the parameters, take the length of that cross product. So that's something you'll see examples of in recitation, guided study group. Okay, so then the last thing I want to do today is just a couple more examples where we really dig into this idea that who cares what the parameters are named. So you can always use UV if you like, but really when you think about it, it's just placeholders, right? This picture that I got here, I could have turned this into A, this into B, this into A, B, A, B, then the whole picture is exactly the same. That the name of the parameter is really just a placeholder. So if there's a different names other than U and V that feel better for you or more convenient, then you might as well use them. So I could think of a few different cases where using something different feels nice. So yeah, in the previous case, you can use X and Y as your parameters, that you don't have to do U and V. I mean, obviously you could, change this to UV, UV everywhere, but yeah, who cares what they're named? So if you want, for certain cases, you could use X and Y. If instead your surface has given to you X as a function of Y and Z, then you could let Y and Z be your parameters. If you're trying to parameterize a sphere, so similar to how we said that coordinates on Earth, on the surface of the Earth, could be latitude and longitude. Well, that's pretty much spherical coordinates. It's the spherical angles. So if you're trying to use parameters on a sphere, you could let the spherical angles be your parameters. You could let r and theta be your parameters if your parameter domain is something that's good in polar coordinates. Or if you're doing cylindrical, you could sort of, in the same way that you could think about the surface of a sphere as you've frozen rho at a particular value, and so theta and phi are allowed to do whatever they want. If you have a cylinder, then you've frozen r at a particular value, and then theta and z are your parameters. So I don't know, let's do a few examples. So parameterize the part of the sphere, x squared plus y squared plus z squared equals 4, above x, z equals 1. So I'll show you 3 ways of doing it. Because, like we said, there's infinitely many correct ways to do this. I'll show you my preferred way. And you're not really going to understand why it's my preferred way until next week. But anyway, I'll just include that here now. So one way is to do this first idea, that we could use x and y as our parameters. So one way would be, to let x and y be our parameters, in which case x and y, in terms of x and y, are just x and y, respectively. And since it says we're on the part above z equals 1, when I go to solve for z, I should take the positive square root. And then, I didn't really call this, but when we do these examples, we'll also make sure that we specify the parameter domain. Because ultimately our goal with all this is to do integrals over these surfaces, in which case we're going to need bounds for our integrals, and so the values of our parameters that give us what we're looking for are going to be very important for getting those integrals ready to go. So I'm going to always, for this, specify what's going on for these parameter values. So to get the part of this sphere, I can figure out that, yeah, I have z equals 1, and then I have this sphere part, which isn't as big as the equator, right? So if you figure out this shadow, the shadow of x and y is not a circle of radius 2, but instead you kind of have to figure out the intersection of these two things, that these intersect at x squared plus y squared equals 3. So you could either, if you're going to eventually convert into polar coordinates after you get going on this integral, I mean, we're not doing an integral today, but you could specify your domain like that. Or if you really wanted to get it ready for integration, you would say that x goes from minus root 3 to root 3, and then y goes from minus square root of 3 minus x squared to square root 3 minus x squared. So you probably don't want to deal with that, but if you did, that's what you would do. That in this situation, our parameter domain is a disk. Okay. So another way to do this is to think like this. You're allowed to use r and theta for your parameters for situations where the parameter domain is convenient and polar. So I could do everything in terms of r and theta. So unfortunately, these two r's are not the same. I have r, my position vector, r, my distance to origin from x, y. But whatever, one of them's a vector, one of them's not. So as long as you're careful, it should be okay. But the big thing, remember, is no matter what, these parameterizations are each of x, y, and z in terms of u and v. So no matter what we're using as our parameters, our equations are always going to be x, y, and z. So if I'm doing stuff like this, I'm really in polar mode. So I could do x is r cosine theta, y is r sine theta, and then z is square root of 4 minus r squared. And then r would go from 0 to root 3, and theta would go 0 to 2 pi. So essentially all I've done is taken my Cartesian parametrization, where my x and y were parameters, and I just replaced, I changed x and y into r and theta absolutely everywhere. So that's another approach you could do. And then another way would be to realize that this is the sphere rho equals 2 in spherical coordinates. So now I could think, okay, well, what are x, y, and z in terms of rho, theta, and phi, and sub in the fact that rho equals 2. So like I was hinting at before, like this is sort of like latitude and longitude. I mean, I'm on the surface of the Earth, or I'm on this sphere where rho is 2, but then my angles are my parameters, so I would have 2 cosine theta sine phi, 2 sine theta sine phi, and then 2 cosine phi. Sorry, I ran out of room, but should be okay. And then for this, theta is going to go 0 to 2 pi. And phi, I guess as usual, we have to play around with this. We've already sort of figured out that this was 3, 1, 2. And so this is what is that, pi over 3 using SOHCAHTOA games. Yeah, cosine of pi over 3 is a half. Yeah. So that's that there. Because remember, from this picture, we don't have the entire top half of the hemisphere. We just have this part up here above z equals 1. And so this angle must be phi equals pi over 3. Okay, but yeah, there's 3 ways to do it. So I think the book tends to prefer the spherical coordinates. I prefer this. So my favorite, because having x and y as parameters will open up shortcuts for setting up surface integrals. So we haven't talked about that yet, but I prefer to do x and y as my parameters anytime that I can. But you don't have to. You could do r and theta. You could do theta and phi. I like sort of like how I showed you with line integrals. As long as you're doing a correct parameterization, the integrals that you get will be equivalent through a substitution. So that's the same story here. But that's my favorite. It's up to you. Okay, so then wanted to do one last one. So parameterize the boundary of the solid bounded by the planes x equals 0, x plus z equals 2, and y squared plus z squared equals 1. So this one's going to be good. We're going to get to really flex our creativity as far as picking parameters, because this one's actually pretty tricky. So let's try and figure out what's going on here. Yeah, I guess I should use black. So I have a cylinder around the x-axis, right? Y squared plus z squared equals 1 is around the x-axis. And so I'm going to cut it off at x equals 0. I'm going to cut it off at x plus z equals 2. So x plus z equals 2 is going to be sort of a diagonal plane. And so let's see here. X plus z equals 2 is sort of going to be diagonal, right? It's going to look like that. So essentially imagine like a paper towel roll that you've cut sort of perpendicular on one side, but then sort of at an angle on the other side. So when you think about it, this solid region, I say we're supposed to parameterize the boundary of it. There's really 3 pieces. There's like a disk on this side, because that's, you know, what are all the points on the edge of this thing, this solid region? Well, I have the left boundary, I have the right boundary, so tilted disk, and then I have the cylindrical side piece. So it's sort of 3 different pieces. So let's call them S1, S2, and S3. And so, yeah, just like I know we've seen examples as far as line integrals go where we had some kind of piecewise definition where we had to split things up. So same kind of story here. So anyway, let's see here. S1, think about it. S1 is a piece of this YZ plane on which x is 0. So x equals 0 is actually a pretty simple formula for x in terms of y and z. Like I said, it's pretty simple. X is 0. So let's let y and z be our parameters on this. So the parameterization for S1 would be y is y, z is z for y squared plus z squared less than or equal to 1. We could do the same kind of thing for S2. For S2, we get something a little bit more interesting. So S2, this tilted disk lives in the plane x plus z equals 2. So x is 2 minus z is our equation for x in terms of y and z. And it's going to be for the same y and z values. And then finally, S3 is sort of the trickiest one. That's why I saved it for last. Let's think of rotated cylindrical coordinates where x is left alone. I don't know, we might have talked a little bit about this, but remember, standard cylindrical coordinates, you leave z alone and you let x and y change to polar. Well, and then so for regular cylindrical coordinates, your cylinders were around the z-axis. Well, there's nothing too special about z. We could always think about cylinders around the x-axis, in which case this would be the thing we do. We convert y and z into polar and leave x alone. And then S3, that's a part of y squared plus z squared equals r squared is 1 for these adjusted cylindrical coordinates. So basically S3, if r is frozen at 1, my parameters are theta and x. And x is just x, then y would be 1 times cosine theta, and z would be 1 times sine theta. So it's sort of like what I did here, where I thought about my cylindrical equations and substituted in rho was 2. I'm thinking about these cylindrical equations, but subbing in r is 1. And then theta would go 0 to 2 pi. It's actually pretty tricky now. On this side piece, this angle theta, how far you are around this circle, determines what x stops at. But x is stopping at 2 minus z. Z is sine theta, so x would go from 0 to 2 minus sine theta. And that would be fine for a d theta dx double integral that the surface integral would become. So I actually pretty much stole this one from a homework problem in next week's homework. So this is the trickiest one. I feel like this last example is for once you're a lot more comfortable with this stuff. But anyway, that's about all I had planned for today. So I will catch you next week. Have a good week and a good day.